Hello class, and this is our video lecture for April the 6th, it's a Monday. So today we're going to talk about titration curves, okay? So from the lab from last week, hopefully you guys are familiar with kind of the general shape of our titration curve. Here you have volume of sodium hydroxide, here you have pH. And so for this part one, we're going to focus on acids. What is calculating pH of acids at the different points in our calibration curve, okay? So for the first part, we're going to specifically talk about strong acids, all right? So these are the ones that completely dissociate, okay? So remember kind of your list: hydrochloric, hydrobromide, sulfuric, but only in the first one, nitric acid, and our perchlorate, perchlorate. There we go, there's perchlorate. So we want to calculate the different points, okay? So we're going to break these into different points in terms of our calibration curve, and we're going to talk about them in terms of their points. So first up, number one, is we're going to talk about that the point before we add any of our sodium hydroxide. What's the initial pH? Okay, so this is the initial. All right. For strong acids and strong bases, they are extremely simple. Okay, because they break completely apart. Whatever the concentration of, say, if you had 1 molar HCl, they break apart. Then you have 1 molar concentration of your protons. Okay? So when we do the pH for strong acids, before we add any, it's just the negative log, and I'm going to write the generic form here, of our acid concentration. That's going to equal our pH. Okay? So that is our pH. Okay? Now, I'm going to continue to run through strong acids, and we'll come back and we'll do weak acids. Okay? So that's the initial pH before you started in. Okay? So let's look at point 2. Okay? So now we've added, well, we'll call this before the equivalence point. Okay? Before EQ. Okay? We've added some sodium hydroxide. Okay? We've neutralized some of the acid. Okay? We want to find out what the pH is. Okay? Well, we still just need to find, for a strong acid, we still just need to find how much acid is left. Okay? So in this case, we pretty much want to take our, whatever our concentration of our acid is, okay? You really want to multiply that by what volume? Okay? So this is the volume of your acid, okay, minus the concentration of how much base you've added, okay, its concentration times its volume. Alright? This gets, so when you multiply your concentration times volume, this really gets you moles. And we'll call that moles of our acid minus our moles of base. Right? So really what we talk about is how much acid is left over. Okay? And we're going to take this difference and then divide this by our volume total. That's going to give us our new concentration. We'll call this like subscript. We'll call it subscript 2 on the outside. So that's our new concentration, okay? Because we actually diluted some of it by adding some base. We neutralized some of it. So then all we have to do is take that new concentration and say pH times the negative log of this HA now 2, and that's going to give us our pH. So this is anywhere once we started adding our sodium hydroxide up to the equivalence point. Okay? That's going to be 0.3 in terms of our calculation. What's going to be the pH when we get to the equivalence point? Okay? Here's, I'm going to make this one really easy for us. Okay? So at the equivalence point, all of our acid has been neutralized. All of our strong base is, we've pretty much used all of our strong base to neutralize it. Okay? So the only thing we really have with a strong acid, strong base is H2O. Which means, in this case, at the equivalence point for strong acids, strong bases only, your pH is going to be equal to 7. You have water, water's pH is 7. That's what you have. Okay? Now the last point for a strong acid, strong base titration is after the equivalence point. Okay? What happens after the equivalence point? So the equivalence point was here, then we come up here and try to find out what happens after we've neutralized all of our acids. Okay? Well, in that case, you don't have any strong acid left. All you have is strong base. Okay? So it becomes a base problem. So to find our pH for base, we often say the POH is going to be equal to the negative log of our OH concentration. And then remembering that pH plus POH, okay, from our lecture notes in terms of our kW of water, equals 14. Okay? So if we wanted to find the pH, then really what we talk about is it's going to be 14 minus our POH. Okay? So all we have to do really is to figure out what our OH concentration is. Okay? So what we can do here is, here again, we can take our concentration of OH, alright, times how much volume you've delivered in terms of OH. In this case, we're going to minus out the acid because we neutralized a lot of that OH with our acid. So let's just take our HA concentration times the volume of our acid. Okay, so this really gets us back to moles. So it tells us how many moles of base are left. And here again, we're going to divide this by our total volume. Okay. Once you calculate that, that is your hydroxyl concentration. Because it's a base problem, you'll often find that we have to do a couple extra steps with base problems. So in this case, when we take the negative log of our OH concentration, that gives us POH. So what we have to do is we have to say 14 minus the POH will give us the pH after the equivalence point. Okay? This is for a strong acid titrated with a strong base. Okay? I'm going to pause it, set it back up, and we're going to run through these same points with a weak acid. Okay? Alright, so let's walk through the different points on our titration curve with a weak acid. Okay? So weak acids are all those ones that do not dissociate 100%. So if it's not a strong acid, it's going to be a weak acid, assuming we're talking about acid. So we have some of the same points that we got to go through. Okay? So first up is kind of what is the initial. Okay? What is our pH before we added any sodium hydroxide? Okay? So this is very simply a weak acid problem. Okay? And if we do our shortcut, okay, so we skip the ice table, we skip our quadratic equation, assuming that we have 2 orders of magnitude difference between our Ka and our concentration, then we can use our shortcut formula to find X. Okay? So X is going to be equal to the Ka times that formal concentration, the starting concentration of the acid. Okay? And X is really going to be our proton concentration. Okay? So once you find X, then really all you have to do is say take the negative log of x. That's going to give you your pH. So this is how you would solve weak acid problems, or figure out in your titration curve what's the pH before you start. So if x is equal to the square root of Ka for that acid times its formal concentration, that's really your proton concentration. Plug that into your pH equation. Alright? So up next is we're going to talk about before the equivalence point. Okay? So what happens when you have your sodium hydroxide? You start neutralizing some of the acid. Okay? So if we write kind of a generic acid, we're going to add some OH to it, and guess what? We're going to produce some of its conjugate form plus water. Okay? Guess what we've now created? We've created the conjugate base acid pair. So now this is really a buffer problem. Okay? Which means to solve buffer problems, we have to use Henderson-Hasselbalch equations. Okay? So remember, that says that pH is going to be equal to the pKa of the acid plus the log of my base over my acid. Okay? So if you have the pKa, the Ka, you can find the pKa, and now it's just a matter of finding the concentrations. Okay? We could do this one of two ways. Most of these problems are set up to where the molarities are very similar in terms of 1 molar, 1 molar, 0.1 molar, and 0.1 molar. So if you know the equivalence point, we can use that kind of as our pseudo concentration. If not, then we can always just calculate the number of moles. Okay? So in order to do this, so if you wanted to figure out what A is equal to, okay, really A is going to be how much of the acid was neutralized. Okay? So take your concentration of your sodium hydroxide times, say, what volume you use. Okay? That will get you your number of moles. Okay? If you want to find out how much of your acid is still left over, okay, we have to start with how many moles of the acid we had to start with. So what is its molar concentration of HA times that volume, okay, and then minus how much was neutralized. So what was that hydroxyl concentration times the volume, and then that will get you your mole ratio of your conjugate base to your acid, and then you can go ahead and calculate it. Okay? Now, a simpler way of doing this is if those concentrations are equal. Okay, so let's say you started with 25 milliliters, okay, of your acid, same concentration, then pretty much you know that your equivalence point is going to be at 25 milliliters. Okay, that's just for this example. It could be 50. That's if the concentrations are the same. You get to the same number of moles. That's the equivalence point. Okay. If you were asked to find the pH, say like at 5 milliliters of sodium hydroxide that was delivered, then all you really have to do is set up this ratio of, okay, I added 5 milliliters, so I put that on top, and then I say 25 minus 5, which is going to be 20. So this 5 divided by 20, that's really your ratio you would put in over here. So you don't actually have to go all the way through and calculate the number of moles, okay, like we're doing here. This is more rigorous, okay, this will work every time. This is just a little simple shortcut that works for a lot of these special cases where the concentration is the same. But basically you're just finding the mole ratio between your acid and your base. Okay? So that's before the equivalence point. That's in this region right here. Now we need to find, we got 3, we want to find it at the equivalence point. Okay? At the equivalence point, we've neutralized all of the acid. Okay? But unlike in our strong acid case where we just created water from those because they were both strong. When you neutralize all of a weak acid, what you end up with is the weak base being present. Okay? So we've converted all of our acid into this weak base. So now what it becomes a simple weak base problem. Okay? So what we can do is we can think about our shortcut type equations. Okay? So for base, our X is going to be our OH, but it's still the Kb, because we're talking about a base problem, over the formal concentration. Now this formal concentration is not what we started with in terms of the acid, but what's the concentration now. Okay? So let me also add that this is my OH concentration. Okay? So to find F, what we really need is how many moles we have. Okay, so take your concentration of your hydroxide times your volume of your hydroxyl concentration. Okay? And then divide this by the total volume. Okay? And for those of you to be a little bit more specific, so this would be the volume of your acid plus the volume of the base. Okay? That's what we talk about when we talk about the total volume. That will get you your formal concentration. This gets you your moles, that gets you your volume, because you've been doing some dilution. You plug that in, this gets you X. Okay, so remember, for base problems, there's always that extra step. So when we do this, we actually find POH. So if we take the negative log of our X, that gives us our POH. And if we wanted to find pH, we got to say 14 minus our POH. Okay? That will give us our pH. Okay? Now we got one more to solve here. Okay? This is after our equivalence point. Okay? So we were right in here at the equivalence point. Now we've gone and we've added a bunch of excess of strong base. The strong base overwhelms that weak base. So really what we talk about is this is just a strong base problem. Okay? So all we have is sodium hydroxide present. So we just need to find its concentration, and then we can take the negative log of that. So really we want to set it up just like we did the strong base or strong acid problem. We want to take our hydroxyl concentration times its volume. Alright? And then we want to minus out how much of our weak acid we had times its volume. Alright? And then simply divide by our total volume. So we've added some more, so find that. This X, we take the negative log of that at X, that's going to equal our POH. And then, like I said, base problems, you always have this extra step, so then you say 14 minus the POH. That allows you to calculate your pH after the endpoint, after you've added excess sodium hydroxide. Okay? So that's the different points in terms of our calibration curve. Finding it before we've added any, finding once we've added some, finding the equivalence point, finding the pH after. We have these 4 simple setups for our problems. Okay? That's all for today. Next time we're going to talk about base. Okay? A strong base or a weak base titrated against a strong acid. They're very similar, but there's some slight nuances that are different. Okay? So I'll post that next time. We'll see you. Take care, and hope everything's going well.